You? Yeah, am I audible to all of you? Someone respond. I need some responses. Am I audible to
Yes,
all of
sir.
you? Yes?
Yes, sir.
Okay. Okay. So let us start. So what we'll start is basically I'll give you a presentation on strain energy. Okay. I hope you can see my screen. So what is strain energy? When a body is what subjected to gradual or sudden impact of load. Suppose a body is subjected to gradual, sudden or impact load. Then the body deforms and work is done upon it. That means what? A body is, subjected to some amount of work, which may be gradual, sudden, or impact load. So this, which may be this kind of free loads, and the body deforms after that, and the work is done upon it. If the elastic limit is not exceeded, this work is stored in the body. Okay? And this work done or energy that is stored in the body is called strain energy. Energy is stored in the body during deformation process, and this energy is called what? Strain energy. Okay? Now, the resilience. So, what is strain energy? That due to sudden impact load that is being applied on the body experiences certain amount of deformation, right? So, because of this deformation, the energy that is stored in the body is called strain energy. Okay? Now, resilience. What is resilience? It is the total strain energy that is stored in the body. Total strain energy means what? It is denoted by sigma square by 2e into what? P. Okay. So the resilience is total strain energy that is stored in the body, and it is what denoted by sigma square by 2e into V. Okay. Where sigma is the stress and V is the volume of the body. That means what? You have to remember these terms. Okay. These terms are very much important. Now after that we will be going to proof resilience. Strain energy stored in the body is called resilience. Proof resilience means what? Maximum strain energy that can be stored in the body is called proof resilience. Now this is denoted by sigma e square by 2e into v. Initially for resilience was what? Sigma square, only stress. Now sigma e square by 2e into v. So sigma e means what? The stress at elastic limit. Why elastic limit? Because at elastic limit only you will be reaching the maximum amount of stress. Okay. So this is called as proof resilience. So resilience and proof resilience, the difference is that only the total strain energy stored in the body is called resilience, and proof resilience is what? Maximum energy which can be stored in the body. Okay. Modulus of resilience. Then we go to the next. So modulus of resilience means what? Maximum strain energy per unit volume at elastic limit is called modulus of resilience. So here, for what happens, for strain energy it was what? Sigma square V by 2E, right? So it was what? It was this resilience, right? Now, if you go to proof resilience, then we have what? In elastic limit, right? And after that, we have what? Modulus of resilience. That means per unit volume. Just remember when modulus of resilience comes, it means per unit volume. That means what? We'll be multiplying this with what? 1 by V. If you multiply this with 1 by V, then why 1 by V? Because per unit volume means what? Like this thing will be what? This this whole red part, you will have to divide it by volume, right? That means we can write it like this, in this manner. Yes or no? We can write like this in this manner. Yes. So what will happen? This V and this V gets cancelled out. So we'll be getting this star. This is the max modulus of resilience. I hope this is clear with every one of you. Okay. Now we'll have some derivations. First of all, strain energy due to Brazil loading. Now for this part, what you'll have to do is you'll have to consider a bar of length L, which is placed vertically at one end and is attached to the what? Ceiling, like this. Yes. Let P gradually applied load. This is P. L is what? Length of the bar. A is the cross sectional area. Delta L. So this is delta L actually. Okay. So this is delta L. This means this is the deflection that is produced. Right. This is the deflection. So sigma is the what? Axial stress that is introduced. Axial stress that is introduced in the bar. Okay, which may be tensile or compressive. That means what? The stress is applied, it may be, tensile stress or compressive stress. Fine. E is the what? Modulus of elasticity or Young's modulus. Right? Now, this work done on the bar equal to area of the load minus deformation. Area of the load minus deformation diagram. That means what? This work done on the bar, the work that is done for elongation, is what? Area of the load deformation diagram. Right. So 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 the work done on the bar is equal to what? Area into deformation diagram. So this is how we will be finding work done on the bar, right? This is the area of the load. That means for half into P into del L. Half, look, one side it is P, right? Half into base into height. That means that area of the triangle is this one, okay? So in this way, you will be finding out. Now this work stored in the bar is equal to what? Area of the resistance deformation diagram. Look, there are two diagrams: load deformation diagram and resistance deformation diagram. So you will have to combine these two. Now resistance deformation diagram half into P into del L. Why? Because del L is the deformation, load is the P, right? Half into P into del L. So for load deformation, for resistance deformation it will be what? Half into R into what? Del L. Look at this. Half into R into what? Del L. Now R is equal to what? Sigma into A. Okay, R is sigma into A. So if R can be written as sigma into A, then we can just equate this work done equal to work stored. Then half into P into delta L equal to half into sigma into A into delta L. That means what? We'll get this relation, which is the what? Stress due to gradual load. So this is how now it is derived. Now look, the strain energy is equal to what? Half into R into del L because of the resistance deformation. That means the strain energy is the different resistance, right? That is offered to sudden impact or deformation. So R means what? Del into A. So R equal to sigma into A. Sorry. So you just write it in this manner, right? Sigma into half into sigma into A into del L. Now del L means what? This one epsilon into L. Now if you combine these, then we will be getting this expression sigma square E by 2v or sigma square V by 2v. Okay. Now there are different cases for sudden loading, then this gradual loading. Okay, we'll go to it. First of all, let us see some videos. Hello everyone.
Alright guys, welcome back. We apply a slowly increasing load to it of P, then we're going to be getting a corresponding deformation. Now we can plot that here welcome back. In this video we are starting to talk about strain energy and strain energy density. So if you imagine that we have a member here of length L with cross-sectional area of A, we apply a slowly increasing load to it of P, then we're going to be getting a corresponding deformation. Now we can plot that here with our applied load on this axis and our deformation down here. But basically, as the member deforms, the load is doing some work, and work is just force times distance. So let's use some calculus, and we'll find elementary work done by P as it moves a tiny distance of dx. So basically, we're looking for this little sliver of area in here. Strain energy is represented as a capital U. So for the elemental work, we just have du is going to be equal to P dx. And if we want to find the total work done to get to this deformation of x1, then we just find the area that's just from x equals 0 to x equals x1. And basically just integrate the area, or find the area under this part of the curve, so we'll be left with just with the integration from 0 to x1 of P dx. Now in the elastic range or straight line section of this graph, the expression for P is just going to be equal to kx. And what we can do with that is when we're looking for strain energy, we'll plug this in, we'll basically substitute P for kx here. So we had 0 to x1, and where we have P, we will write kx, and then we had dx. Alright, so kx is a constant, so we're going to bring that out. So from 0 to x1, we have x dx, and this simplifies just to 1/2 k x squared. Now we should put in the subscript here of x1 because we substituted in here x1 and 0, but the zeros obviously just disappeared. So now we have x1. Now, talking about this though, kx is equal to p, and what this is really saying is we have 1/2 k x1, right? That's just squared. So if kx is equal to p, then we can rewrite this as 1/2 p1 x1. So this is our expression for strain energy, where we have strain energy is equal to U is equal to 1/2 p1 x1. And basically the strain energy of a member is just the increase in the energy due to the deformation of that member. And the other thing to mention is that strain energy is in units of joules, which is newtons times meters. And when we look at that, that's what we do have. We would have newtons here times meters. So for strain energy, this is all based on a member with length L and a given cross-sectional area. But in order to be able to talk about members with any dimensions and like basically compare apples to apples, we need to divide by the volume to get strain energy density, which is going to give us the energy per unit volume. For example, this will be in units of like joules per meter cubed instead of just joules. All right, so let's give ourselves some space, and what we want to do is basically work with this expression here, and we want to divide out the volume to be able to get strain energy density. So let's just put this over volume, and we'll put this over volume, or in this case, because this is some kind of rod, we can say this is the cross-sectional area times the length. Now, when we look at this, we have some important things here. We have P over A in this side of the expression, and that's just equal to our normal stress. We also have, if we look at X over L, that's the normal strain. So if we have X over L, that's equal to normal strain. And if we have dx over L, as we do in this expression, that gives us basically our little elemental strain, just like that. So we can substitute some of these things in. And when we talk about capital U over V, this is strain energy density. So this actually drops down. We can say that, I'm going to write it over here, capital U over volume is equal to lowercase u, and this is equal to strain energy density. So we can go and substitute some of these things in here now. So we'll write this as lowercase u, and we'll have our integral here. When we'll substitute P and A for, or P over A for our normal stress, and then we'll substitute this here for the elemental strain there. And then this means that we'll have to go from 0 to strain to E1 there, or epsilon 1. But we also have Hooke's law, where we have the normal stress is equal to E times epsilon. So we can plug that in here as well and rewrite this. So we're going to get strain energy density is equal to 0 to epsilon 1 of E times epsilon x, and then we have d epsilon x. Okay, so we'll pull out the capital E here, as it is a constant. So we have E is equal to 0 from 0 to epsilon 1 of Ex dEx, and this basically just simplifies to 1/2 E epsilon x squared. Now, with Hooke's law, again, we have, we can just rearrange this. So we have epsilon x is just going to be equal to normal stress over E, just like that. So basically what we can do is we can substitute that in here. So we're going to be getting 1/2 E, and then we'll just substitute all this stuff in. So that was squared. So we have squared over that squared, right? It's coming from us right there. And we can simplify this. We have 1 E in the top, 2 in the bottom. And then let's just rewrite this a little bit cleaner. So we'll have sigma x squared over 2E. So that is our strain energy density. That is on a per unit volume. So we have, again, we'll just write it here a little cleaner. So we have sigma x squared over 2E. And if we go right up to the end of the elastic section, then we're just going to find what's called the modulus of resistance, which is basically the strain energy density once we are all the way to the yield point. So that's just going to be sigma y for the yield point, or the yield stress, and that's over 2E. So basically, if we just draw the stress strain diagram for this, for whatever material we're looking at, it's going to look, it's going to look something like this, right? You'll have the linear elastic section, and maybe if it's steel or something, something like that. But if we basically plot this area in here, or calculate the area in this section, this is what we call, so we've gone all the way up to the yield point. This is basically what we call the modulus of resistance. And this tells us the energy per unit volume that a material can absorb before it yields. And then if we went right to the end here and took this area all the way from 0, then this is what we call the modulus of toughness, which tells us the energy per unit volume that a material can absorb before it ruptures. So those are two very important things based in these equations, and I think that's where we're going to cut it off for this video. Join me in the next video, and we will go through some examples on this stuff.
Hello everyone. So last time we were discussing the properties of the material. So to understand the next property, let's first understand strain energy. So let's first write the definition of strain energy. So it is defined as the internal work done to deform a body by the action of externally applied forces. So according to this definition, what is strain energy? It is the internal work done to deform a body. So to understand that, let's say we take a steel bar and we apply this load P on it. So this load is gradually applied here. That is, initially it is 0, then it increases to P. So what will happen inside this material or inside the bar? Because of this load, there will be stresses in the material, and let's say there is a deformation of delta L in this bar. So that is, strain will also be there in this material. Now let's try to write the external work done. External work done due to this load P. So work done is nothing but force times displacement. So force here is changing from 0 to P. So average force we can write is P by 2 into displacement is delta L. That is your work done, that is external work done. Now if we assume that there is no energy loss, or in other words, if this is a perfectly elastic body, then we can say this external work done is equal to internal work done. So as per this definition, internal work done is nothing but the strain energy. So this becomes the strain energy as well. So strain energy is denoted with U. So U is equal to 1 by 2 P into delta L. So this is one form of this equation. We can rewrite this equation to get other forms. So this load P, we can write it as stress into area, and delta L we can write it as strain is equal to delta L by, change in length by original length. So from here, change in length is equal to epsilon times L, that is epsilon into L. So from here we get U is equal to half sigma epsilon, and A into L is nothing but the volume of the bar or volume of this material. It is AL. So this is V. So this is another form here, and we can further write it in another form, that is this strain we can write it as stress divided by modulus of elasticity. So from that it becomes half sigma square upon E times volume. So this is another form of this equation, and there is one last, that is U is equal to half. Now we can write this stress as P by A. So P square by A square E into the volume is again A into L. So from here U is equal to P square L upon 2A. So these are the various forms of this equation. Now why we are interested in this strain energy? Because if we are talking about an elastic body, then this elastic body has a property. It can store this energy when some external force is applied and this energy can be recovered when this external force is removed. So this energy becomes usable to us. That's why we are interested in this strain energy. So based upon that, the next property is defined, that is resilience. So resilience is the property due to which a material is able to store energy without having permanent deformation. That is, the material when strained or when the load is applied, this material can store the energy, and this energy does not cause that permanent deformation, because when this load is removed, then this energy is released and this energy can be used. So this type of action is used in case of spring. So this resilience property is very useful to find out which material would be better for the spring action. And so to quantify this resilience, there is this modulus defined, that is modulus of resilience. So the strain energy what we derived previously, it can also be derived from the stress strain curve. So because we are interested up to this elastic limit, because that's what the energies which can be recovered. So the area under this curve here gives you the strain energy as well. So that is, the area would be half stress times stress. So that is the strain energy per unit volume, because earlier we defined strain energy as this half epsilon E into volume, this one here. So here we can say this is the strain energy per unit volume, and this strain energy per unit volume is nothing but the modulus of resilience. After that, next property we have toughness. So toughness is the property due to which the material can withstand impact loading without fracture. That is, the material can be strained, but it will not produce strain but no fracture. So the material which can take more strain without fracture will be the tougher material. So to define toughness, there is this modulus defined, that is modulus of toughness. So again, in the stress strain curve, let's say if we take the stress strain curve up to the fracture, this last point, and this area here, area under the curve, so that gives the modulus of fracture, that is the strain energy stored up to fracture per unit, or we can say divided by the volume of the material. So that's how modulus of toughness is defined. So which material would be tougher? The material which can take more strain up to fracture. So with that logic, the ductile material would be tougher than the brittle material. So with that logic, mild steel would be more tough. Mild steel would be tougher than cast iron.
So I hope the concepts are clear today.